Hello everyone, I'm Norman Walberger, and we are talking about diffusion symmetry, which is an alternative sort of orientation towards symmetry in mathematics and physics. And the main objects that we're looking at are hypergroups or related things. And I want to explain to you today about how these things come about in the context of geometric lattices. And we started talking about the square lattice in 2 dimensions, and ultimately we're going to be interested in higher dimensional lattices as well, like a face-centered cubic lattice in 3 dimensions, or even very interesting lattices, D4 lattice in 4 dimensions, E6, E7, E8 in 6, 7, 8 dimensions. There's a Leech lattice. So there's all kinds of interesting extensions of these ideas. But we're going to start actually at a more elementary level today. Okay, so let me just remind you, with the 2D lattice, we identified that the traditional symmetries of such a thing, in terms of group theory, involved a point group. So if we specify one point, say the origin, then we could talk about the symmetries of the object which maintain that particular point. That's a finite group, which in this case we call D4, or just D. And then there was a lattice group of translations. You can translate one to the left or right, or one up or down. So that gives us a translation group, sometimes called Z2. And together then these things form a space group. So we can act by translations or by these point motions. And so we get what the chemists call the space group. Now that's from the traditional group theory point of view. And the natural question is, can we look at the same story from the hypergroup point of view? And the answer is yes, we can. And in fact, actually, we can do that at several levels. But in order to explain that, it's simpler actually if I go to 1 dimension down to a very simple lattice, which is the integer lattice. And a lot of the discussion about that will be of a kind that generalizes quite easily to these higher dimensions. So it's going to be really useful. You're going to find out lots of sort of useful techniques having to do with matrix theory and semi-direct products that allow us sort of to get a good handle on the classical symmetries in such a situation, and then allow us to move on towards the hypergroup diffusion symmetry story. So here is the 1-dimensional integer lattice, just consisting of the points on the number line with integer entries. And there's also a point group and a lattice group here, which are very easy to describe. The point group, say if we concentrate on the point 0 and ask, well, what are the symmetries of the lattice that preserve that point? Well, there's only 2. There's the identity element and a basic reflection that just interchanges the positive and the negative values. So E of n equals n for any integer n, and R of n equals minus n. And we could call this little 2-element group D2. The lattice group is just also very easy, just the group of translations. So translations of the form T sub k, where T sub k of n equals n plus k. We're just shifting by a fixed amount. And then to describe the space group, which is a combination of these 2 things, well, it's a semi-direct product of the point and the lattice group. So we have to explain what a semi-direct product is. And we're going to do that using the 1-dimensional affine group. So there's a theory of geometry here that's underlying the story, and we can use some linear algebra associated to the affine group, giving us what's usually called the AX plus B group. And that's a nice place to frame this discussion so that we can see these groups naturally appearing inside the AX plus B group. So this is very important and useful point of view because it extends very nicely to higher dimensions, and in particular to those other lattices that we're eventually going to be wanting to look at. Okay, so let's introduce the affine group, consisting of 2 by 2 matrices of the form 1b 0a, where both a and b are rational numbers, but a has to be non-zero in order for that to be an invertible matrix. Now, such a matrix will act on the affine line once we make a slight change of notation. So instead of thinking about a point on the line as a single coordinate x, we can think about that as being encoded by the pair 1, x. This is really somehow sort of taking a projective point of view, adopting projective coordinates in this setting. So the advantage in that then is that this 2 by 2 matrix can then act on this, if we think of this as a row vector. So we do this product and we get 1 plus 0, that's 1, and b plus ax is ax plus b. So the action of this matrix will take this point, basically the point x, to the point ax plus b, hence the name ax plus b. Now these matrices do form a group. Okay, their product is something of the same kind. So if we take this product here, we get 1 times 1 plus 0, there's 1, and 1 times 0, and 0 times it, that's 0 there. This one here is b2 plus a2 times b1, and this bottom one here is just product of a1 and a2. And it's also closed under inverses, so the inverse of 1b0a is 1 minus b a inverse, and an a inverse down there. So this is the affine group, and this is how this affine group acts on a point. And you see that it's a combination of two things. It's a combination of a scaling factor, just multiplying by a, takes the entire line and sort of scales it, positively or perhaps negatively, or maybe sort of shrinks it. And then combining that dilation with a translation. So that's a general affine transformation. And in one dimension, that basically encodes affine geometry. Now, for our purposes, there are two important subgroups of this affine group. The group of just translations, matrices of the form 1b01, that's easy to see, that's a subgroup. And also the matrices that just reflect the dilation symmetries. So 1, 0, 0a, where again, a is a non-zero rational number. So these are subgroups, and they have a particular relation to each other. So in group theory, we talk about normalizers and normalizing. And in this case here, the subgroup A normalizes the subgroup B. Let me explain what that means. It means that if you take an element of B and you conjugate it by an element in A, that means you're multiplying on one side by an element and by the inverse element on the other side. So here's an element of B, here's an element of A, and here's the inverse of that element. So if we take this product, let's do this product first. Well, that's 1, 0, B, 0, 0, and A. So in fact, we get the general element in our affine group by taking a product of this element from A and this element from B. Now the inverse of this element here, this matrix, is 1, 0, 0, A inverse. And then when we do this product, we get 1, 0, and here B times A inverse, or A inverse B. And bottom here, just 1. So in other words, we're getting another element of B. So we started with an element in B, and we performed this conjugation, and we got another element of B. So in group theory language, that means that A is normalizing B. Another way of saying it is that A is a subgroup of the normalizer of B. Or another way to think about it is that we have an action, a conjugation action of A on B. Because now if we take any element in A, say this one here, then we can act on elements in B to transform them to other elements in B. Now there's a way of restating this which is also kind of useful. If we bring this inverse here over to the right-hand side of this what's here, then we get the product of these two matrices is equal to this one times this matrix on the right. And so this is telling us how to go from a product of an A matrix and a B matrix to a product of a B matrix and an A matrix. Actually, the same A matrix works, but we need a different B matrix. So remember, in group theory generally, we're talking about non-commutative groups. So this is a non-commutative group. So, the product matters which way we order things. And this is then a kind of a nice aspect of it, which really is at the heart of the semi-direct product construction. So this is what's called a semi-direct product, where you have the entire group is A, B. In other words, it's the product of the two groups. We've seen that because any element in the affine group is a product of an element in A and an element in B. And in fact, there's no intersection other than the identity. So the common elements in these two groups, there's only one, which is the identity matrix 1, 0, 0, 1. That's the only element that's common. And And sometimes in group theory language, the semi-direct product is written like this. The affine group is A, semi-direct product B. There's a kind of a triangular symbol there, which is suggesting that there's a normal subgroup floating around here. So B is actually a normal subgroup of the big group. That's another way of saying what's going on here. Okay, so this is a semi-direct product construction of just the affine group generally. So the advantage of having this matrix set up is that now we can describe the symmetries, the classical group theory symmetries of a lattice, not just in terms of sort of geometrical descriptions, in terms of, well, reflections in this line or translations by that, or or glide reflections given by these things. We can alternatively now describe the transformations in terms of matrices. And this gives us a sort of a uniform language and a technology so that we can do arithmetic in these groups much more easily than without it. In some sense, this is the heart of what's called representation theory. Okay? Representation theory, what you're trying to do is to represent a general algebraic object by matrices, typically. Okay? Once you have sort of identified this abstract algebraic thing with matrices, well, then you can work with matrix arithmetic, which is very convenient. Our computers are very good at it, and we have a lot of routines and technology and understanding of how the linear algebra of matrices works. Okay, so now we can get back to our lattice, our integer lattice, let's call it L, and we can now describe the symmetries of this thing in terms now of these matrices, the affine group of matrices. So the space group now consists of things which are translations, and also which consists of these point reflections. So we can create two groups, okay? These are sort of analogs of the A's and B matrices, but they're inside the subgroups A and B that we had before. So here we're just looking at those A-type matrices where there's either a 1 or a -1 down here in this corner. Okay, so it's just a two-element group. And so that's going to have the effect of taking an element x and either sending it to x or to -x. Now, N is a subgroup of the B subgroup that we were talking about, where we are restricting this entry here to be just an integer. This ensures that this group will act on our lattice to sending points in the lattice to other points, because we're always only adding an integer value. So the AX plus B action of these things on the lattice really does preserve the lattice. And so now if we take the product of one like this and one like this, well, we get a matrix that looks like this. It has a combination of a translation component and a dilation component. Well, the dilation is either multiplying by 1 or -1. So this is then the space group of this integer lattice. Okay, so we have a nice representation of all the elements in our group. And just as we had some relations between the A and the B group, well, that's now inherited by these subgroups. So D normalizes N and acts by conjugation. So we do the same kind of thing that we did before, but now sort of with these specialized cases. We take this particular entry here with an N here, that's an integer, and we conjugate by one of these. So there's only two possibilities, so I'm going to do both of them at the same time by putting a plus or minus 1 here. So if I put a plus or minus 1 here, and this plus or minus 1 is supposed to be the same as that one. So if this one is plus 1, then this one is also plus 1. And if this one is minus 1, then this one is minus 1 as well. The reason is because the inverse of 1, 0, 0, minus 1 is also 1, 0, 0, minus 1. Okay, so when we restrict to these two simple matrices, the inverses are the same as those matrices. Okay, so then when you do this product, you get 1 plus or minus n, 0, 1. So you can see that the action of conjugation is just sending one of these n matrices to another n matrix. The only difference is that perhaps the entry here has changed sign. Okay, so now let me bring in the diffusion symmetry aspect of this story. So it turns out that this integer lattice, which is ongoing in either direction, is very much analogous to what's happening on a regular polygon in terms of a diffusion symmetry kind of approach to the graph. So let me remind you that we looked at the pentagon case earlier as an example. And we saw that as a graph, we could think, if we say starting at C0, we could think about subdividing the vertices into three sets, C0 itself, and then the things of distance 1 from C0, which is calling C1, and then the things of distance 2 from C0, which are these 2 points here. And it's these three sort of sets of vertices that form the associated hypergroup, or fusion rule algebra, depending on how we normalize things. So let me remind you that we had an algebraic structure, which was of this kind. We call this the golden hypergroup. It's actually a very special kind of case, where C1 squared was 1/2 C0 plus 1/2 C2. And the meaning of this is that if we start here and take a random step of size 1, so either end up here or here, and then from wherever we are, we take another step from that point of size 1. So let's say we're here at the first step, then our next step either sends us to here or to here with equal probabilities. So we have a 1/2 chance of being at C0 and a 1/2 chance of being in C2. And similarly, there's a relation between C1 and C2, the product there, and C2 squared. So what I'm saying now is that over here in this lattice situation, we have a very analogous story. And in fact, what we end up getting is something which is in some sense an unbounded version of these polygon kind of hypergroups that we could look at like this by extending the number of vertices. This one has 5 vertices, but we could look at the same thing with 6 vertices, 7 vertices, 8 vertices. And somehow there's a sort of an unbounded object which is sort of beyond all of them. And that's this thing here. So let's have a look at the same kind of story now. We're thinking about starting at the origin. We're going to call that C0. And we're going to think about essentially a random walk on this lattice. So, you're there. And at each stage, you get to choose, am I going to go left or right? Left here, right here, okay? And maybe you flip a coin. Fair coin, so you have an equal probability of going left or right. That then results in a random walk. And that's exactly the same kind of thing that we're doing here, except that now the random walk potentially could go very far in that direction or very far in that direction. It's not sort of bounded by the geometry of the configuration. So just as in this case here, what ends up happening is that from the perspective of C0, this diffusion has a symmetry. After one step, we could be either at this point or at this point. And so it's convenient to lump those two together. Okay, and call that C1. And then these 2 points here, both of distance 2 from C0, they form what we call C2. And then these 2 points are going to form C3 and so on. So we're going to have all these, an unbounded number of these elements now. And what is going to be the algebraic structure that goes with this? Well, we're doing exactly the same thing that we did over here and in all these other examples. So C1 squared, you ask the same question. Well, if I start at C0 and I take a step of size 1, okay, maybe I'm either here or here. Let's say I'm here. And then from there, I'm going to take another step of size 1. So I'm either going to end up at C0 or I'm going to end up in C2 with equal probabilities. So I write 1/2 C0 plus 1/2 C2. How about C1 times C2? Well, you can think about taking a step of size, say, C1. Okay, there we are there. And now from there, we're going to take a step of size 2. Well, that will take us either to this point here or to this point here. Okay, that point or that point. So where are those 2 points? Well, this one is in C3, and this one is in C1. So we end up with a 1/2 chance of being in C1 or a 1/2 chance of being in C3. What about C2 squared? Okay, so if we take a step of size 2 first, and then from there another step of size 2, well, there's a 1/2 chance of being back at C0 at the end of that, or there's a 1/2 chance of moving to C4. So we get an unbounded kind of hypergroup now. So it's a little bit different It's not a finite thing anymore. It's unbounded. But it still has a lot of the sort of algebraic structure, sort of parallel in some sense to these kind of hypergroups. So this is very interesting because random walk on a one-dimensional lattice, or even more interestingly in higher dimensional lattices, is a very interesting thing, okay, and much studied. And so this is a way of accessing that from an algebraic point of view, using this hypergroup or diffusion symmetry kind of orientation. So we get an object now, which is an unbounded hypergroup. Let's call it K, and it consists of these elements C0, C1, C2, etc. One for every natural number. And here is a slight reconfiguring of that one-dimensional thing where I'm kind of folding the left-hand negative numbers up in this direction here, making it just a little bit easier to see, where the C's are, and also making it a little bit more parallel to what happens in the polygon case. Okay, so here's like the point that's usually called 0, 1, 2, 3. Here's -1, -2, -3. I've just got them going up that direction. That doesn't make any difference as far as this algebra is concerned, because all what really matters is the connectivity, which vertices are connected to which others, in terms of the neighbors. And when we do this, then C1 is just clearly identified to be those 2 points. C2 is this set of points. This C3 is a set of points. So nice. Okay, so this hypergroup that we're getting here is called Hermitian. It's an example of a Hermitian hypergroup, and that means that the star, or the antiparticle, if you like, of any of the elements is itself. And I remind you that means that, say, if we are wanting to multiply C2 by something in order to get a non-zero probability of getting C0, then we have to multiply C2 by C2. If you're at C2 and you want to have at least a reasonable chance of getting back to the origin on your next step, you have to take a step of size 2. A step of any other size is not going to give you a possibility of getting back to C0. So we say that the star of C2 is itself. So that's a special property of a hypergroup that it has. That's a very important property because a lot of hypergroups have that property, but not all. Okay, and here are the structure equations, okay, that cover basically all the cases. If we have some Ci, I is just a natural number from 0, 1, 2, 3, etc., and Cj is another natural number, then here is what happens. When we take Ci times Cj, what is happening is that there's two things that we can do. Let's say we're starting at I, okay, we've gone to I, and now we're going a step of size j. Well, there's two things that can happen. We can either go backwards and take I minus j, okay, but if I and j are both positive, so it might be that I minus j is negative. In that case, because all these elements here are indexed by positive natural numbers, we have to take the absolute value to get back into the range of natural numbers. Okay, that's why there's an absolute value here. And the other possibility is to add the j to get Ci plus j. And these have equal probability, so that's the basic equation. So there's really only one structure equation, and that happens even with if I equals j. If I equals j, then there's a C0 that's appearing here, so that's the star condition. So it's actually a very simple and elegant hypergroup, but it's surprisingly interesting and quite important. Okay, so now we're going to ask a very natural question, which is what's the probability of being at some particular element C sub k after n steps? So starting from the origin, or C0, and we're taking n steps, and the steps are all of size 1, just like we've been talking about. What's the probability of getting at C sub k? So this amounts, as we've seen before, in just basically evaluating this power. We're really asking, what do you get when you take C1 to the n in this algebra? And I'm going to work through some of the low-dimensional examples, and I'm going to leave this to you as an exercise to try to figure out what the general case is. It's a very interesting and illuminating exercise, I think. Okay, it's well worth spending some time at, and I'll reveal what it is in the next lecture. But okay, so let's go through the possibilities. When n is equal to 0, then C1 to the 0 is just C0. We haven't gone anywhere. If we take one step from C0, well, obviously we're at C1. So it's C1 with probability 1. Okay, when n equals 2, if we take a step of size 1 and then another step of size 1, well, 1/2 chance of being at C0, 1/2 chance of being at C2. So things get a little bit more interesting when we look at C1 cubed. So we can think about that as C1 times, here's C1 squared. We're just copying that. And now we use the distributive law. Okay, C1 times C0. Well, C0 is the identity, so that product is just going to be C1. So we're going to get a half C1 here. And over here, we get 1/2 of the product of C1 times C2. What was that? Well, you can either take the difference, which is 2 minus 1, that's 1, or you can take the sum, which is 2 plus 1, which is 3. And there's an equal probability of getting either of those. So then when we do a little bit of arithmetic here, there's a half C1 here, a quarter C1 from this term. So altogether 3/4 C1 and 1/4 C3. If you take 3 steps, okay, then at the end of that you have a 3/4 chance of being somewhere in C1 and you have a 1/4 chance of being somewhere in C3. Okay, let's go a little bit further. C1 to the 4th. Well, we could take just C1 times C1 cubed. That's what we just got. So when we do this first product, we get 3/4 of the product of C1 with C1 is 1/2 C0 plus 1/2 C2. The product of C1 and C3 is 1/2, the difference is C2, and 1/2 the sum C4. So there's a quarter here. So when we do that in one step, we get 1/8 C2 plus 1/8 C4. And now we can combine things here because altogether there's 3/8 of a C0. And in terms of C2s, there's 2 contributions. This one is 3/8 from here, and here's 1/8 from there. So a total contribution of 1/2 C2 and a single 1/8 C4. And just to check, the sum of these things is indeed 1. So yes, still maintains the probabilistic aspect, which is at the heart of things. All right, so now let's go one step further to C1 to the 5th. C1 times what we just obtained, and then what the product is. Well, C0 times C1 is C1, so we get 3/8 of that. This product here is 1/2 of C1, C2, so that's 1/4 C1 plus 1/4 C3. And this product here, there's a 1/8 here, so we'll get 1/16 of C3, the difference, plus 1/16 C5, the sum. And then we put these together. There's a 3/8 C1 here. There's a 1/4, which is the same as 2/8, so a total of 5/8 C1. C3, so you use 4/16 and 1/16, so 5/16 C3 plus 1/16 C5. Okay, so that's kind of interesting, right? So if you take a random walk of size 5, starting at the origin, after 5 steps, you've got a 5/8 chance of being at distance 1 from where you started. You have a 5/16 chance of being at distance 3 from where you started. You have a 1/16 chance of being at distance 5 from where you started. So a very natural question is, can you find a general formula for C1 to the n? That's a nice exercise. So in the next video, we're going to talk about that, and I'm going to introduce a major new connection with algebra in a different way that allows us to solve this kind of problem. So thanks a lot for listening, everyone. And I would like to take the opportunity of thanking all my subscribers, but especially I'd like to thank members of my channel and also Patreon supporters, especially longtime Patreon supporters. So I'd like to give a special thanks, shout out to David E., to Leo G., to Frank R., to Ronnie A., to Doug G., to Hedwig V., to Daniel P., to Alan G., and to Samarinder S. Thanks so much for your support. It's really appreciated. So look forward to you joining me in my next video. I'm Norman Wahlberger. Thanks for listening.